Your rate limiter logs show each Redis node accepted 1,000 requests per hour, but the global aggregate hit 2,000 per hour. No single node saw a spike, yet the total rate doubled. The root cause? 30 milliseconds of clock drift between Amazon Web Services regions. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover design a rate limiter. A rate limiter controls how many requests a client can make within a given time window. Without one, a single misbehaving client can saturate your backend, causing cascading failures. The fixed window algorithm divides time into discrete intervals. It's the simplest to implement but allows bursts at window boundaries. If the limit is 1,000 per hour, a user can send 1,000 at 11:59, 59, and another 1,000 at 12:00, 2,000 requests in 2 seconds. Here's a basic fixed window implementation. It uses Redis INCR and expire. Note the warning, this is not atomic at high concurrency. For production, use the Lua script provided in the article. The sliding window log stores a timestamp for each request in a sorted set. It provides perfect precision, but memory grows with request volume. At 1,000 QPS, a 60-second window stores 60,000 entries per key. This implementation uses a Lua script to atomically remove old entries, count remaining, and add the new request. It's precise but memory-intensive. The token bucket algorithm maintains a bucket with a capacity for bursts and a refill rate for sustained average. It's memory-efficient and ideal for most production APIs. This Lua script calculates tokens to add based on elapsed time, caps at capacity, and deducts one token if available. It's atomic and O1 memory. The sliding window counter tracks 2 counters per key, current window and previous window. It computes a weighted average to approximate the sliding window without storing per request timestamps. This implementation uses Redis time for a consistent timestamp across nodes, avoiding clock skew. It's memory efficient and production proven. Where you place the rate limiter matters. Edge limiters protect against DDoS but lack per-user nuance. App limiters provide fine-grained control but consume compute. A hybrid approach works best. The edge limiter uses Redis for IP-based global rate limiting. The app limiter uses an in-memory store for per-user quotas. Each has its role. A rate limiter has 3 components: a rule store for configuration, a counter store for tracking requests, and a decision point that checks counters against rules. Redis is the preferred counter store for its speed. This decision point is stateless and uses Redis for counters. Rules are cached and refreshed periodically. If Redis is down, it fails open. Functional requirements define what the system must do. Reject excess requests, support multiple time windows, expose rate limit headers, and allow hot reloading of rules. This protocol defines the functional contract, is allowed, remaining, and reset time. Every rate limiter should implement these. Non-functional requirements constrain the design: sub-5 ms latency, high throughput, and high availability. These eliminate heavy algorithms like sliding window log for high-traffic APIs. These hard limits drive algorithm choice. For example, 5 ms latency rules out heavy log-based approaches. This is the same issue we highlighted at the start. Here's exactly why that happened. The rate limiter used local node time for window calculation. Node A's clock was 30 ms ahead of Node B's. A request at 12:00:00:000 on Node A and another at 11:59:59, 980 on Node B fell into different windows on each node's local time. Both were accepted, allowing 2x the intended rate. The fix was to use Redis time command to get a centralized timestamp, ensuring all nodes use the same time for window calculation. They also implemented sliding window counter and added clock drift monitoring. This prevented the 2x traffic issue. For high-traffic APIs, sliding window log consumes too much memory. At 1,000 QPS, a 60-second window stores 60,000 entries per key, which can quickly exhaust Redis memory. At high concurrency, 2 threads can read the same count and both increment, allowing more requests than the limit. Always use a Lua script to make the increment and check atomic. Using local node time in a distributed system causes clock skew. Nodes with different times may assign the same request to different windows, allowing double the intended rate. This is the exact line that caused the incident. Using local time in a distributed system leads to clock skew. Always use a centralized timestamp like Redis time. The article mentions using Lua scripts for atomicity, but only shows a non-atomic Python example. Here is the complete, production-ready Lua script for a fixed window counter that atomically increments, sets expiry, and returns the count. The article warns about clock skew but doesn't mention that Redis clusters, Redis time, returns the time of the node you connect to, which may still have drift. For cross-region clusters, use a single leader node for time or use the cluster time command to get a cluster-wide consistent timestamp. Alternatively, use a token bucket algorithm that doesn't depend on absolute time windows. The article describes token bucket conceptually, but only provides a Python class without the Lua script. Here is the atomic Lua script for token bucket that calculates tokens based on elapsed time, deducts if available, and stores state. The article mentions fail open and fail closed, but doesn't discuss the trade-off in depth. In production, a common pattern is to fail open with a degraded mode. Allow all requests but log and alert. This avoids blocking legitimate traffic during a Redis outage while still providing visibility. For security-critical endpoints, fail closed is preferred. Always test your failover behavior with chaos engineering. Use these commands to diagnose rate limiter issues. Check clock drift between nodes, verify your code uses atomic operations, monitor Redis memory, and ensure low latency. Let's run through some common interview questions. Fixed versus sliding window counter trade-offs. Fixed, simple 2x burst. Sliding, 0.1 memory, -1% error, no boundary bursts. Distributed rate limiter surviving Redis failures. Consistent hashing, replica reads, or local token bucket with periodic sync. What happens when Redis is unreachable? Fail open, fail closed, or degrade to local limiter with relaxed limits. And a few frequently asked questions. Rate limiting versus throttling. Rate limiting rejects success. Throttling slows down processing. What key to use for rate limiting? API key user ID IP. IP is easily bypassed by proxy pools. How to choose window size? Match to SLA, 1s for DDoS, 1 min for moderate, 1 hour for quotas. To recap, choose the right algorithm based on your traffic and precision needs. Always centralize time in distributed systems and use atomic operations to avoid race conditions. Ready to go deeper? Up next, design a notification system, then design a search autocomplete, then design a payment system. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.